Dear students, I myself is Dr. Rajshekar Reddy, Assistant Professor of Mathematics, Government First Grade College, Pavagada. Now we discuss third semester BCA Mathematics. In this, we go for Unit 1 Matrices. So in the previous sessions, already we have learnt about the basics in matrices, how to find determinant, adjoint, then inverse of a matrix. Then we discussed about the linear equations and Cramer's rule of solving linear equations. Then we discussed matrix method of solving given system of linear equations. Then we discussed consistency and inconsistency. Now we go for Caylay-Hamilton theorem. So Caylay-Hamilton theorem states that every square matrix satisfies its characteristic equation. Every square matrix, already we know about square matrix containing same rows as well as columns. The number of rows is equals to number of columns. That square matrix satisfies its characteristic equation. So already we learned eigenvalues and eigenvectors. In that one we know the characteristic equation is determinant of matrix A minus lambda I is equals to 0. Determinant of A minus lambda I is equals to 0. So such characteristic equation, in such characteristic equation, A represents the given matrix, lambda be a scalar and I be the identity matrix of same order of the given matrix A. So to prove this one, first we should know about the matrix polynomial. So any expression of the form lambda m into lambda am into lambda to the power of n plus am minus 1 into lambda to the power of m minus 1 plus so on plus a1 into lambda plus a naught. So here am minus 1, a1, a naught, all these are the matrices of same order. So am minus 1 and so on a1 comma a naught, all these are the matrices of same order. So if these are the matrices, then only the expression am into lambda to the power of n plus am minus 1 into lambda to the power of n minus 1 plus so on plus a1 into lambda plus a naught represents a matrix polynomial of degree n in lambda. Matrix polynomial of degree n in lambda. To prove the Caylay-Hamilton theorem, first we take capital A represents any square matrix of order n. A represents a square matrix of order n. Then we take the matrix polynomial. So already we know about matrix polynomial. Here directly we consider the characteristic polynomial. So what is the characteristic equation? Determinant of a minus lambda I is equals to 0. But here we take only characteristic polynomial, that is determinant of a minus lambda I. So this a minus lambda I we can express in the form by expanding that one. We get minus 1 whole to the power of n into c naught into lambda to the power of n plus c1 into lambda to the power of n minus 1 plus so on plus cn, where here c naught, c1 and so on cn are the scalars. So now the characteristic equation means determinant of a minus lambda I is equals to 0. That is c naught into lambda to the power of n plus c1 into lambda to the power of n minus 1 plus so on plus cn is equals to 0. So this is the characteristic equation. Now we prove that this characteristic equation satisfies, that means a square matrix satisfies this characteristic equation. That means replacing lambda by a, we have to prove that condition. That is that So in the place of lambda matrix A appears, it should satisfy. That means we have to prove that C0 into A power n plus C1 into A to the power of n minus 1 plus so on plus Cn into I is equals to 0 matrix. So here I represents identity matrix or unit matrix. So already we know adjoint of A minus lambda I, adjoint of A minus lambda I, also expressed as a polynomial of degree n minus 1 in lambda. That's why adjoint of A minus lambda I, we can take that Bn minus 1 into lambda n minus 1 plus Bn minus 2 into lambda power n minus 2 plus so on plus B1 into lambda plus B0. Here B0, B1 and so on, Bn minus 1 are the matrices of same order n, and their elements being a polynomial in terms of Aij. Already we know in adjoint A into adjoint of A is equals to determinant of A into I. So this one we discussed while discussing adjoint of a matrix. A into adjoint of A is equals to determinant of A into I. Therefore, A minus lambda I into adjoint of A minus lambda I is equals to determinant of A minus lambda I into I. So that implies A minus lambda I into adjoint polynomial Bn minus 1 into lambda power n minus 1 plus Bn minus 2 into lambda power n minus 2 plus so on plus B1 into lambda plus B0. That is equals to minus 1 whole to the power of n into C0 into lambda power n plus C1 into lambda power n minus 1 plus so on plus Cn into I. Now equating both sides, left hand side and right hand side, like powers of lambda. Equating both sides, the coefficients of like powers of lambda. Then we get minus Bn minus 1 is equals to minus 1 whole power n into C0 I. A into Bn minus 1 minus Bn minus 2 is equals to minus 1 whole power n into C1 into I. Like that, finally we get A into B0 is equals to minus 1 whole power n into Cn into I. All these conditions we multiply both sides by A power n and adding. All these equations, first equation we multiply by A power n, second equation we multiply by A power n minus 1, third equation we multiply by A power n minus 2, and finally we multiply by I, and adding all such equations. Then we get that C0 into A power n plus C1 into A power n minus 1 plus C2 into A power n minus 2 plus 1 plus Cn into I is equals to 0. That means it is a matrix polynomial. So already we know the characteristic polynomial. We have taken that C0 into lambda power n plus C1 into lambda to the power of n minus 1 plus so on plus Cn is equals to 0. Same way, the similar way, in the place of lambda, we proved that A appears. In the place of lambda, A appears. That's why we say that a very square matrix satisfies its characteristic equation. Determinant of A minus lambda is equals to 0. Based on that, we can say that Caylay-Hamilton theorem is proved. So always we remember Caylay-Hamilton theorem states a square matrix, every square matrix satisfies its characteristic equation. Now to verify Caylay-Hamilton theorem for the matrix 1 1 2 1. So first row 1 1, second row 2 1. For this one, first we have to write the characteristic equation. The characteristic equation is a determinant of A minus lambda I is equals to 0. So taking that one, we get the polynomial in terms of lambda is lambda square minus 2 lambda minus 1 is equals to 0. Now to verify whether Caylay-Hamilton theorem satisfies or not, in the place of lambda we take the matrix A. So we prove that A square minus 2A minus 1 means 1 into identity matrix I is equals to 0. Now we find A square, matrix multiplication, A into A. We get that A square value, A matrix, first row 3 2, second row 4 3. Next we calculate 2A matrix. It is 2 2 4 1. Again we verify A square minus 2A minus I is equals to, so A square value we know 3 2 4 3 minus 2A matrix we know 2 2 4 2 minus identity matrix 1 0 0 1. So matrix addition and multiplication, if we take the resulting, we get that 0 0 0 0, that is null matrix. Hence we say that the matrix A satisfies its characteristic equation. So every square matrix, if any square matrix satisfies its characteristic equation, we say the Caylay-Hamilton theorem is proved. Same here also we have to verify the Caylay-Hamilton theorem.